Okay, I think we're ready to start. So, welcome to EE 123, lecture 12. Woo! Introduction to wavelets. Yes! I'm all hyped. Before this, I just wanted to show you, I have to say, Frank, your model TA did an amazing job in creating the lab, and that's a video I just took outside of a screenshot. Your real-time, the real-time lab, the ADS-B lab, which is basically picking up signals from airplanes. You're going to decode the packets into bits. And then Frank wrote a wrapper that will take those bits, interpret them, get the information of the position of an airplane, also the flight number, and then display them on Google Maps. So here's just a screenshot where it picked up an airplane just west of San Francisco, and the airplane is moving, so we're getting more packets, and it's being updated. And I think it's United Airlines 1255. United Airlines 1255. Okay? And some of you got in like way more airplanes. And so during the day or morning, evening, you'll get tons of airplane signals, especially if you're here. And you'll be able to monitor them and see them on a map once you get that to work. Okay? Again, like everything with this IPython, sometimes it just doesn't work. So you need to just restart. Okay? But I think this is definitely, I think it's pretty nice to actually see. It's quite incredible that you can do this with a $10 device. Normally, to get ADS-B equipment costs thousands of dollars. Okay? Because it's aviation. Okay. All right. Okay. So last time we talked about the short-term Fourier transform, Heisenberg boxes, and today we're going to move towards wavelets. And it's really an introduction to wavelets. We're not rigorously going through wavelets. I just want you to understand what that means. That there's other types of time frequency analysis that are more optimal or more adapted to different type of application. So you'll get a sense of what is actually out there. And when you take graduate level classes, you kind of know what they're talking about. One announcement is that I put a Piazza post on the amateur radio exam on March 12th. Please register at the East Bay Amateur Radio Club website. Fill in the form. You'll need to sign up with the FCC for an FRN number. It doesn't cost you any money. You just go and get an FRN number, which basically will replace the need of you to fill in your Social Security number when you go to the register for the exam, because you don't want to give your Social Security number. So you get an FRM number from the FCC, and that identifies you to the FCC, okay, when you get the exam. So fill in this, please, as soon as possible. I gave your names to the Amateur Radio Club. They'll give you priority of taking the exam. Yes? If you read the post, it says that if you have a conflict, please put that on the website and let me know about that. And then we'll try to fit in with, we'll accommodate that somehow. Okay? But we'd like everybody to go in through by 8:15. So we know that there's enough time for you to go through it. Okay? It does take time. Any more questions about that? How was the midterm? That's not too bad. Well, we'll see when you get things back. The only one that's keeping the midterm from being fully graded is me. The rest of the staff did their work. Apologize for that. Okay. Yeah, you guys have an amazing TA. So be really proud to have them. They're the most fantastic I've ever had. Okay. So let's move on. Time frequency decomposition and time frequency tiling. We talked about the discrete short time Fourier transform, and we showed that the time frequency tiling is effectively these boxes, same area boxes that we break the time frequency to. And for each part of the time frequency space, we have the same size box. Okay? We can move these boxes around by zero padding or by, for example, having overlap boxes and so on and so forth. They can move around almost continuously to that way, but they're still the same size boxes, no matter where you are in time and no matter where you are in frequency. Okay? All right. So one of the limitations, though, of the short time Fourier transform is that you need overlapping in order to do a reconstruction. So if we want to do operations in the short time Fourier transform, we need to overlap so we can reconstruct it in a stable way. It is computationally more intensive, so it's Mn, which M is the size of the window n log n, right? Because we're doing lots of FFTs. But we also have the same kind of Eisenberg boxes. They're always same time frequency uncertainty. Okay? Even if you have a slow changing signal, we're going to look at the same time resolution. If you have a fast changing signal, we're going to look at the same time resolution, same frequency resolution. So the question is, can we do something else? Okay? And the basic idea that leads into a type of a wavelet or a multi-scale type of a decomposition is that if you look at low frequency components in natural occurring signals, they tend to be slowly changing. Okay? If you have some phenomena that produces something that has low frequencies, it doesn't change abruptly from one low frequency to another. Often it just behaves, just as slow changes over time. So fast tracking of this type of changes is not necessarily very important. Okay? But if you want to be able to distinguish between these changes in low frequencies, you need better frequency resolution. Okay? So you don't need that time resolution so much, but you need a good frequency resolution to see those changes at all. Okay? But if you have fast changing stuff or high frequency type of phenomena, often that does change fast, and maybe we need a way to track it faster in time. So the question is, can we adapt the Eisenberg boxes such that it fits to this type of a need? So instead of now having the same exact size, can we change them? And so this is what a wavelet decomposition really attempts to do, is to break the time frequency space into different sized tiles. Well, different shaped tiles. Again, the area is going to be the same, but they're going to have a different shape depending where they are in time and frequency. Okay? So they represent the signal better. So what we're going to do now is just going to go for back to continuous time for a little bit when we talk about wavelets, and then we're going to go again to discrete and look at discrete time representation. And one thing that you'll see that we're going to get to, once we start talking about sampling, and then we get into multi-rate signal processing, we'll kind of come back to those ideas that I'm going to teach you today. Okay, so you're going to see it again in a couple of weeks, okay, from a slightly different perspective. Okay, so I think by then you should be able to get a really nice picture. Okay, so let's try to move from short time Fourier transform to wavelets. So if you look at the continuous time and you look at the short time Fourier transform, it's basically an integral over a window. Basically, it's a Fourier transform over a window. Okay, so you have you have a time signal. It is multiplied by a window, and then you compute a continuous time Fourier transform. And then you slide the signal, keep the window in the same place, and then do another continuous time Fourier transform. And then, of course, you do that for every point on the continuum. Okay, so you've got every point on the continuum. So it's not really computable, right? When you compute it, then you have to evaluate it on, let's say, a grid or certain points. But this is the continuous space. Much like time is continuous, this is also continuous. And it's continuous both in time, which is u now, and omega, which is the continuous frequencies. Okay? So the continuous short time Fourier transform is a mapping from one dimension, which is time, into a two-dimensional space, which is both time and frequency. Okay? Much like we saw in the discrete case. Okay? And it has these Eisenberg boxes that you have some uncertainty in time that correspond to a certain uncertainty in frequency. All right. Instead, what we're going to do is a slightly different decomposition. Look, it's actually not that different when you look at the formulation. Okay? Formulation here is that you'd have effectively this, what we called a kernel, okay, or a basis function that is multiplying our signal. This is a window, and this is a frequency. So we have a window with oscillating frequency in it. What we're going to do then is we're going to change this. We're going to replace this kernel here with a wavelet kernel. And what it is some function that I'm going to tell you what its properties, that you shift it around. You shift that function around, much like you shifted this window, right? You shift this window around. You can shift this function around. But instead of having a frequency, what you do is you stretch it. So you modify S. S scales the function. So you think of a class of functions that has a certain shape, and we take this function and we multiply our signal and integrate over them, and we do that over shifts and all possible stretches and shifts. With a short time Fourier transform, we had a constant window, and we would that we move around, and we would change the frequency inside that window. Right? That's what the Fourier transform is, the short time Fourier transform, right? Constant window that we shift around, and we just change the frequencies. So that's how we map from one-dimensional space into two. There's the position, and then there's the frequency. Now we're going to take some function, and we're going to move it around the same way and take basically inner products, or multiply our signal and integrate over it. It's an inner product. And then we're going to stretch it like an accordion. And stretching has some relationship to frequency. Because if you take a sinusoid at a particular frequency and you stretch it, now it is lower frequency. If you squeeze it, it's a higher frequency. It changes faster. Okay, so there is time and frequency information here. Okay? And the way that you write it is you write it as this kernel, that is shifted and is stretched. So we map now, instead of u and omega, so time to u and omega, like here, what we do map is to u, which is the same thing, and to s. S will be scaling, the stretch. Okay? Does this make sense? And this is due to Morley and Grossman. Okay? Now, what this leads to is, if you look at the tiling of the time-frequency space, what you're going to get is that for the low frequency, you're going to get less uncertainty in frequency and more uncertainty in time. And for the high frequencies, you're going to get less uncertainty in time, but more uncertainty in frequency. Okay? So a lot of these things I'm going to say now may look abstract, but at the end, you're going to compute something, and I want you to see what does that lead to. Okay? So this is effectively the wavelet transform. There are certain rules about the kernel, or what we also called the mother wavelet. Okay? There's rules of what it could be, and it could be not just one type of function. Actually, there's a class of functions that you can use. So it's a little bit more rich than just a Fourier type of kernel. Okay? And the function is called a mother wavelet. And there's two things that it must satisfy. The first thing is that its energy, or its norm, is 1. Okay? So if you look at its norm, it's going to be 1. The other thing is that it has 0 DC. Okay? It doesn't have any DC component. Okay? So if you integrate, it will be integrate over it. It has 0 area. Okay? So in fact, this is kind of like a bandpass filter. Right? It's not a low-pass filter. Okay? Does this make sense? And in fact, what you'll see is that really the wavelet transform are a bunch of bandpass filters. In fact, these are what wavelet coefficient will represent, coefficients of bandpass filters. But we'll get to that. So if we call this a mother wavelet, a kernel, we also call these atoms. Okay, why you call them atoms? Because molecules are made of, atoms that you combine them together to get something. Here you take basically basis functions and you add them together to get functions. Okay, so this is why the word atom appears in this type of a context. Okay? So what is a short time Fourier transform atom? Okay? If we use the Hamming window, multiply by a Fourier kernel, this is for high frequency, for omega that correspond to high frequency, a short time Fourier atom looks like this. It has a real and imaginary component. The real, and each one of them are shifted by 90, like they're 90 degrees shifted in phase. So cosine plus I sine, effectively. And so it's a windowed frequency. Right? It's a windowed complex frequency. And this one is a high frequency. So it is finite in time, okay, because of the window. And then because of the U's, we shift it around. And we try to build our signal decomposition by basically a linear combination of different shifts version of this with different shift versions of other frequencies. Okay? So this is one atom. A shifted version of it would be another atom. Another shifted version would be another atom. Okay? And if we also look at the same position, we can look at an atom which represents a lower frequency. Okay? That will correspond to a omega which correspond to a low frequency. So this would be kind of like 2 cycles within this range. This would be many, many cycles, or I don't know, like 10 cycles within the same range. Okay? So across all possible shifts, across all possible frequencies, we'll try to find kind of a linear combination that would give us our signal. Okay? So this is really the time frequency, the short time Fourier transform. If we just did a Fourier transform, then we didn't have the window, and we just had a constant frequency everywhere, and we would just vary those frequencies, and we will try to find a linear combination of all these frequencies that would lead to our signal. Now, we are using slightly different atoms, which are also compounded in space. Okay? So these are the basic components of the short time Fourier transform. if you notice, they have the exact same size in space. Same support. That gives us a certain resolution and frequency. It just determines it. So that's why these boxes are the same when you look at the time-frequency tiling. I'm talking really slow for you to digest what I'm trying to say. This takes time to understand. What does it mean? I mean, look, this is like Legos, right? You can buy a house, or you can make a house out of Legos. And in Legos, you can have different components that you can kind of go and build them together. These are the Legos that you buy for the set of the short time Fourier transform. If you want to build any shape in time and frequency, you take these components, you add them together with different weighting, and you'll get your signal. Okay? It's a basis. Okay? But this is one basis. And if you want to make like a really nice looking spacecraft, some Legos are not good for this. Some that have better resolution, will make a nicer spacecraft, right? With less components maybe. Like you just buy the Legos with the spacecraft. Right? Because these are better basis functions to represent a spacecraft. Right? So, but you could still buy something, that would look like a spacecraft, but it's not as nice. Okay, so again, if you want to use the same number of components, then if you want to make an approximation of a signal, some will be better, some of them not. Yes?
Is the SDFD a type of wavelet transform?
Short time Fourier transform.
Is it one of the wavelet transform?
It's actually not just a wavelet transform because it doesn't have the scaling thing. It is just a shifted version of frequencies. Okay? Now we're going to lead to a different type of atoms, which are the wavelet atoms. Okay? And wavelet atoms look like this. Okay? S correspond to scale. So you start with a scale 1. You pick up a scale. Okay? This is scale 1. That's the highest, representing the highest frequency. It's the most compact. Okay, 1. And that's its shape. And now I'm going to have this Lego elements that I'm going to combine these atoms into something, into actually my signal. But these ones are made of these components that are shifted. And then if I want to go, so now instead of changing the frequency within a constant size window, what I'm going to do is I'm going to stretch this particular signal. I'm going to stretch it. And here I stretch it by a factor of 3. Okay? So for S equal 3, the scaling, I'll get this function. Obviously, this kernel basis function atom has a lower frequency component than this one. Do you agree? How do you know? What's the most easiest way to actually do that, to actually figure that out? Right, there's that property too. But you can just compute a Fourier transform and see this. But you're right. When you stretch something in the time domain, then it does the opposite thing to the frequency domain. Okay? So there's the inverse proportionality. If you scale something in one domain, it squeezes in the other domain. And that's exactly what's happening. We stretch over time. Now we have more time support too, but our frequency content squeezed. So we lost uncertainty. We lost certainty, or get more uncertainty in time. But we have better uncertainty in frequency. Okay? So that's the difference between these decompositions. There's just different components, but they are corresponding to frequency. So the S's have relationship to frequency, but they're not pure frequency. They're scales. If you think about this, it's kind of like looking at, like the if I look at this classroom, and then I zoom out, right? Then I look at the entire building, and then I zoom out, and then I look at like Berkeley, and then I zoom out. I look at the West Coast, I zoom out. This is kind of the same effect that we're going to be dealing with. We're going to look at different scales of a signal. So there's different types of wavelets. People have come up with lots of them. And they're different. And they're better for representing certain type of signals. Here's one called Mexican hat. I wonder why. It's basically this function, 1 minus t squared, e to minus t squared over 2. This is actually has an infinite support in time. But it decays really rapidly. So it is kind of localized in that sense. But it does have an infinite support in time. Okay? The window is not completely zero everywhere. Okay? It does satisfy the requirement that I had before. It is localized, though, in space, right? Most of the energy is localized here. So this is one function. Here's another function. This is a Haar wavelet. And this is actually the wavelet that we're going to be discussing. It's the simplest one. And it's really easy to compute in discrete time. Okay. The Haar wavelet is defined as minus 1 between 0 and half, and 1 between half and 1. Okay? So it looks like this. Obviously, this is a bandpass filter. How do I know? Well, because it doesn't have DC. And then eventually, at the highest frequencies, like if I really go for high frequency, everything is just going to cancel. Right? If I just put lots of cycles over here, then everything is going to cancel. Because they're going to be exactly as this too. Because this is constant, if I have a full cycle of a sinusoid, and I have enough of them that are really, really squeezed, I'm going to get 0. And obviously, it is a kind of just 2 rects, right? So rects also decay to, with 1 over x, 1 over f, or 1 over omega. Eventually they decay. Right? So just 2 shifted rects. Okay? So it is a bandpass filter. So let's look at a decomposition, actually. Let's look at how it looks. Remember when I showed you a spectrogram of a bird chirping? That's pretty obvious, right? There was time, there was frequency. It was pretty obvious. How does a wavelet look like? We have U, and we have S, and we take some signal. So let's take a chirp signal. Chirp, we did labs with it. We talk about chirp. Chirping's fun. How do chirps look like in the wavelet? Well, what's the chirp in the short time Fourier transform? You look the first slide in my of the class, EE123. Right? That's how it looks like. Okay, it's just a line. Okay? It's a diagonal line because you increase frequency versus time linearly. So how does a wavelet look like? This is a wavelet of a chirp. I think this is a Mexican hat. Okay? This is S. That's scale. And this is U. Time. Or position. Okay? Scale and position. So look what's interesting. Okay? Here's what's cool. So a chirp changes frequency over time, right? let's look at the resolution of details that we can see. Right? You see that for the low frequencies, we're kind of able to distinguish. We actually see them. For the low frequencies, look at kind of what is the resolution that happens over time. I mean, it's quite wide. There's not many changes over here, right? Compared to a short-time Fourier transform, we would have completely left this, right? So there's not enough time. As we go for the higher frequencies, you see the details of the signal. You see the time details of the signal in the high frequencies. We don't see that in the short-time Fourier transform. In the short-time Fourier transform, we just see a line. We don't see actually the signal changes over time. Right? We don't have the fine details. We're just the same thickness of line everywhere. Okay? And here we're able to see structure, in the high frequencies. This is actually a cross-section showing this. So for the finest scale, for S equal 1, I'm showing you a cross-section of U. You see there's a lot of structure that we see. If I just showed you the short-time Fourier transform, you would just see kind of a block here, right, for the high frequency. And as I move down, I kind of start losing spatial information, but I'm getting more and more resolution and frequency, okay, as I move down. So it kind of makes sense. If you think of a signal that was more complex than a chirp, that had things that are changing that we'd like to track, they're changing fast, we'll be able to see them. But we'll also be able to see, for example, if there was a global trend, we would see them in the fine scale. In the coarse scale, which is the bigger S. So the difference between the two would be something that looks like this and something that looks like this. Yeah, we don't have very good frequency resolution in the high frequency. We don't have. But we can see how things are changing in time. That's always the trade-off. We won't be able to distinguish between a high frequency and a slightly higher frequency. Not possible in the wavelet transform. But we'll be able to see those actual changes in time. At the same time, in the low frequencies, we'll have a very, very fine resolution of small, tiny frequency changes, but we won't have, if those change rapidly in time, we won't be able to see. But because it's low frequency, it doesn't happen. So here's an interesting signal. Okay? This is, again, a Mexican hat. This is the signal that I have. It's constructed out of bumps and small low-frequency changes. Okay? So there's jumps, which have high-frequency components, right? Jumps. And then there's a low-frequency information that's kind of like, this is low-frequency. And the whole thing is kind of like low-frequency if you think about this. If you zoomed out, and you would go a few hundred meters away, you won't be able to see the small changes, right? You kind of see a trend. This is exactly what I'm showing you. This is the wavelet transform. As I zoom in, I see those bumps. You see the bump? It's much more obvious on my screen, by the way. Okay, so it's the contrast here is not that great. Let me see if I turn the light off. Oops. A little bit. So you see the bumps? Each of the bumps are high-frequency changes that we'd like to see them where they happen in time. Right? And we know exactly where they're happening. That would never happen in the short-time Fourier transform. We always will have this uncertainty, no matter if it's higher or lower frequency. Now we know, hey, it occurs here, 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 it occurs here. As we go down the scale, so we go to coarser and coarser, what we get is kind of like a zoomed out version of what we see. So we see more global changes, okay, that occur. And actually, if you think of the information in the signal, is really kind of along these ridges of the signal. That's where information lies. And then at the end, if I look at the coarser scale, what it really represents, it represents the kind of global trend, low pass, right, of my signal, right? Kind of like becomes bright, and then becomes dark again. So it goes up and goes down. So we're kind of looking at different scales of that signal. Okay? But it gives us a lot of information about it, much more detailed than we would get, for example, if we use a short-time Fourier transform. Okay? These bumps in a short-time Fourier transform would correspond to basically, everything would be filled up. Okay? So what's going on there? I don't know. You'll have a block. As you pass this block, it's like, oh, okay, it's all bright. What's the details there? I don't know. Okay. So this is the advantage of using this decomposition. Yes?
Do you have a comparison of two different wavelets of the same signal?
I'll get to that. Now the wavelets differ from, the different shapes. So this is a Mexican hat wavelet. If you think of a Haar wavelet, how it would look like, Haar wavelets are, really good to representing piecewise constant signals. Okay, so whenever you have something that changes like really rapidly, piecewise, Haar wavelets kind of fit well. If you think about these blocks trying to fit in something that looks like buildings, you'll be like perfect, right? But if you try to represent something that is a little bit curvy, you'll need a lot of small coefficients, and it's not going to represent that well. Mexican hat is kind of more like smooth, so it's actually really good at representing those changes as well. It doesn't need that many. And the bumps will be a little bit wider than you would get for a Haar. So it will smooth a little bit those bumps. But it's all trade-offs. Okay? And I'll talk about which class of signals is kind of better. I'll mention this a little bit. Okay, any questions? Yeah.
Are there lower values of S going up, or is it just going down?
Now, we pick a scale 1, and we start from that. Yeah, S is increasing that way. Yes?
Why did you take the log of S?
Oh, it's just so I show that. So it's a log scale of S. So S goes from 1, and this is, I don't know, like 100 or something. So it's not like linear.
Is that better for showing the structure in the previous?
Yeah, it was just easier to show. It just squeezes the thing. I used also a package, it's called WaveLab, that displays it that way. So there's packages that you can use that compute those, and it's better for visualization. If you actually think about it, every time you scale by a factor of 2, it kind of cuts it to half. So instead of that, I just show that in a log, so it kind of makes more sense. So the wavelet transform can be written that way, but it could also be written as a filter type of operation. I mean, what is this? This is some kernel. It's a function, right? That for a particular S, I perform a convolution with. Right? I mean, this is almost exactly what a convolution defined as, right? T minus U, fix S, forget S. Let's say S equal 1. This will be almost a convolution, except you didn't flip the signal. Okay? So this is how a convolution is defined. So effectively, you can define it as a convolution with the flipped version of it. Okay? So it is where this is actually defined this way. Okay? So it is can be described as basically linear filtering. Okay? Short-time Fourier transform, by the way, can be described in the same way. You can take those short-time Fourier kernels and then convolve with them. Shift the windows, right? It's the same thing. Here, we can do it the same way. So wavelet coefficients are really a result of bandpass filtering. Different bandpass filterings. Okay? So you run your signal through bandpass filters, you get something, and here is the continuum, so all possible S's, all possible U's, right? It's continuous space. Right? So that's great. But there's a lot of bandpass filters that you can use, right? And each one will have different properties, will work maybe better or worse. So there's many construction for different signals. So Haar wavelets are really good for piecewise constant signals. You would need very few coefficients to represent something that looks blocky with blocky type of basis functions. If you have something that's made of splines, okay, splines are polynomials that are stitched together with some continuities between them. If you have something that is represented this way, then you should maybe use bandpass filters that are constructed from splines. And one of them is Vattel-Emery spline polynomials. Lots of French, by the way, mathematicians contributed to that field. So Daubechies and many others. So this was continuous, but it was not orthogonal. Okay? We started from one dimension, one axis, one variable, and we ended up with two. And there's overlap between wavelet coefficients. Right? They're not orthogonal to each other. If I look at a small shift between a certain wavelet kernel and another wavelet kernel, they have an inner product between them. Okay? They're not orthogonal. But we could make them orthogonal. We could, instead of having a continuous shift, we could shift them in jumps. Okay? So these are continuous functions. Omega are continuous functions, but we don't shift them continuously. We shift them in jumps. And we can still construct a signal out of them. Okay? And if we make those jumps, for example, if we do that dyadic, so we make sure that there's no overlap, and we set the scale to be also dyadic, so 2 to the power of I, then the function can become orthogonal. And here's an example. This is orthonormal Haar. What I'm showing here, each color represents a different atom. Okay? And instead of having, for that particular scale, all the possible shifts of atoms on the continuous scale, I'm just going to have atoms that are non-overlapping. If they're not overlapping, they're orthogonal to each other. Because if you multiply and add, then they don't overlap, then it's 0. And then if I go to the next scale, if I scale that exactly by a factor of 2, then if you look at this guy over here, will fit exactly within a positive lobe. So if you have negative, positive, same area, multiplied by something that's constant, you integrate over that, still gives you a 0. Right? I multiply this with this particular function. So it only overlaps with this area, but it is positive and negative, so it integrates to 0. So now those functions are orthogonal. So now we've got an orthogonal transplane by the fact that we are now shifting by non-overlapping, and we're scaling by factors of 2 all the time. Okay? So now we can call it, basically we have these scaling functions. So these are now our wavelet atoms in the orthogonal case. They're represented by I and N. I is the scale, N is the shift. Okay? I is the scale, N is the shift. This used to be S. Now S equals 2 to the power of I. This used to be U. Now, instead of U, I have 2 to the power of I times N. Okay? So for the courses scale, where s equals 1, I equals 0, then this is 1, this is 1. I've got shifts of 1, 2, 3, 4, 5, 6, 7. Okay? For the scale where I equals 1, then it's scale s equals 2. S equals 2. Now I jump every 2. For s equals 3, I jump every 3. Actually, there's no 3 because 2 to the power of I. S equals 4, and then s equals 8, and s equals 16, and s equals 32, and s equals 64, and s equals 128. Okay?
So, in order to make them orthogonal, the scaling has to be, in a sense, discretized. Right?
Yes. The scaling is discretized, the u is discretized, but these are continuous functions. Okay? They're still continuous functions. When I add them together, they become continuous. I mean, you can think of, a rectangular which is continuous plus another rectangular which is continuous. You add them together, a continuous function. You only shift them in discrete cases, right? So they're still continuous. Now the problem is that if you think about, let's say for s equal 1, s equal 1, which is I equal, basically the finest scale, okay, the finest scale, those represent a certain part of a bandpass. As I increase the scale, then effectively what I'm doing is I'm separating the space into high frequency and low frequency. And then I split that into a high frequency and then low frequency. And then I split that into high frequency and low frequency. And then I split that into high frequency, low frequency. And I can go on and on and on and on and on and zoom in and like zoom out, zoom out, zoom out, zoom out, zoom out, zoom out. But it's never going to end. I need infinite number of functions to represent something. Okay? So every stretch covers half the remaining bandwidth. And so I need infinite functions in order to represent the entire frequency space. And that could be a problem. So the solution is basically, what do you do when, what could you do? I cannot use this function in this form to represent the entire space without having infinite number. So if I cannot not use this form to represent infinite number, I'm going to ask a friend. If mommy cannot do it, we're going to ask daddy. Okay, so there's a mother wavelet, and there's a father wavelet, which basically is a plug. Okay, so we're going to decide how far we're going to go with a stretch, and then we're going to do a low pass a function which has a low pass component. So all these are bandpass, 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 bandpass. They're getting close to being low pass, but they never are, by definition. Then we're just adding a plug, which is a low pass. And that enough to represent the entire space. So, if this is a mother wavelet for HAR, the plug, or the father wavelet, is a box. Okay? This is high pass or band pass. This is the low pass. Okay? So next time, what we're going to go is, how do we translate those ideas into the discrete domain? So in the early 80s, there's a lot of theoretical work in the field of wavelets, basically mathematics. In the field of mathematics, Morley, Grossman, Meyer, they came from math and geophysics and developed a lot of theory. In addition to this, there was a whole slew of work by engineers that develop filter banks type of processing, break the signal into bandpass filters, okay, and then do operations there. And in the late 80s, there was a link to this DSP work from this mathematical work by Dobishi and Mallah. And then they came up with a really nice unified theory of those all ideas and how they connect together. So the question is really, how do we go from this continuous time representation into a discrete time? By preserving still all the properties, let's say orthogonality, being able to represent things, and the plug, and being able to reconstruct things. And it turns out it's not so trivial. And you have to really pay a lot of attention when you go for this discrete case. And so, what we're going to do then in the next lecture is to talk about one representation of discrete, which is the discrete Har, and how you can perform the decomposition, but also perform this very efficiently, in order of n type of calculation, which will lead to the discrete wavelet transform. Okay. And I'll see you on Wednesday. Thank you so much.